Okay, here we are at lesson 4 of the relations unit, unit 5. Um, okay, so quick review of the number system. Each letter, well, how do I do this? The N represents the natural numbers. Those are the counting numbers, 1, 2, 3, 4, and on, okay? The W represents the whole numbers. So that's all of those. Oh, let me do this in color. Let's do it this way. Blue. So W is the whole numbers, which is all of the natural numbers plus 0. And then we have the integers, which is the I, which is all of those plus their negative counterparts. Okay, so it's all of our counting numbers and our negative counting numbers. So it's basically the full numbers from negative infinity to infinity, but just the full numbers, okay? And then we get to the Q, which is the rational numbers. And the rational numbers is, the definition of a rational number is a number that can be written as a fraction of integers. So the formal definition is it can be written as a fraction of integers where A and B are integers and B is not equal to 0 because you cannot divide by 0. So that includes, so rational looks like 3 over 4, but that's equivalent to 0.75. So those are both rational numbers. So a rational number, does it tell us here? Yes. No, it doesn't. The important thing about a rational number is you can write it as a fraction, so it can be positive or negative. You could have negative 7 over 9. But when it looks like a decimal, the decimal ends like that one there, or it repeats. For example, if you do 1 over 3, that's a rational number because that's a fraction of integers, and that equals 0.3 repeating. Okay, so those are all rational numbers. Okay, and the symbol for that is Q. And then the other group of numbers is the irrational numbers, and it's a logic symbol that this it's Q bar. The Q with a bar over top means not. So the irrational numbers are all of the numbers that are not rational, and that means you can't write them as a fraction of integers. And if you write them as a decimal, they never end or repeat. So for example, that's like pi. Okay, you know that pi just goes forever and ever and ever. Another example would be the square root of 2. Because we can approximate the square root of 2, but we can't write an exact decimal that represents that, okay? So, but then in contrast to that, the square root of 16 is actually a natural number because the square root of 16 equals 4. So that's just a different representation of 4, so it still is a natural number. And then you've probably seen the diagram where there's this nesting thing that happens. So the natural numbers is the smallest set of numbers. It's infinite, but it's still smaller because the whole numbers includes all of the natural numbers plus the 0, so it's bigger. I know the idea of there being different sizes of infinite is kind of mind-boggling, but there you go. And then the integers is even bigger, right? It's actually twice as big as the natural numbers because it's all of the natural numbers and their negative counterpart. And then so every whole number and every natural number is also an integer. And all of those are also rational numbers. No, wait a minute, I have to put a box around that one because you'll see why in a second. Okay, so there is, that was a terrible box. Let me try that again. Okay, so that is all of the rational numbers, okay? And then beside that, we have another box, which is the irrational numbers, okay? And the irrational numbers, believe it or not, there are more irrational numbers than there are rational numbers, but the box is always smaller because it there's only one type of number in it, so we don't make it a big box because there's not as many things that we need to write inside it. But anyway, both of those groups are infinite, and then those together make up the real numbers. Oh, I wanted to red for that. Oops. Ah, what did I do? Sorry, hit the wrong button. Red. Undo. Okay, and red. So the real numbers, this is the real numbers. So the real numbers is all of those numbers. Okay, so basically every number you've ever seen in your life is a real number. They are, there is another set of numbers that are called the imaginary numbers or the complex numbers, but you don't deal with those at all in high school. I'm not even sure you do it. Yeah, you do it in first year university. If you do calculus, you must, because I know I saw them there. They use them a lot in engineering, but the rest of us don't ever use them. Okay, so there's your overview of the number system. I'm just looking ahead to see if there's an example of the box. No, never mind. Okay, on to the next thing. Domain and range. Now this is a really, sorry, there was a couple other things that I needed to cover on this page. Sorry, up here. So, and I'm sorry, I've drawn over it. This is what happens when I try and do this in a hurry. Right here, this is important. This symbol here, I messed this up. It's this little, we call it, we read it as E, but it's actually like a half circle with a little line on it. And that represents the phrase, is an element of. And then we use the brackets, the curly brackets, like that. And that represents the set of all. And so that is the set of all elements that I'm describing. Okay, let's do some examples of that because that I realize doesn't make any sense at all. So let's go on and do some examples with this. Okay, domain and range. Domain of a relation is the set of all values that can be used for the input or the independent variable, which we often, X is our default value. And range is all the Y or the output values. So conveniently, we always do our ordered pair as X, Y. And so this is the domain, and this is range. And they're both in alphabetical, like X, Y is alphabetical, domain and range is alphabetical. That's how I would remember which one is which, okay? And then there's lots of different ways that we can describe our relations, and there's different ways that we can write out the domain and the range. So in this first example, we're just given a list of numbers. So the domain, of course, is the X value, or the first one, and the Y, the range is the Y. So for the domain, we're just going to list all the X values. We're going to list them in order, numerical order, and we're going to do them in, we only list each number once. So the domain, we go D colon. So the domain is the set of numbers. I've got -3, 5, 3, 0, and 1. So I'm going to write that -3, 0, 1, 3, 5. So that is the domain. And do the range in a different color. So the range is all of the Y values. So if I put those in order, it's the set of numbers 2, 5, 8, 9. Okay, and over here, note each number listed only once. Okay, if it shows up twice, we only list it once because we just want the list of numbers. We don't need to know it. If we're just saying the domain and range, we don't care how many times each is used. We just want that list of numbers. All right, and then for this one, the domain X, so the domain is -8, -3, 0, 2, and 3. And our range is 3 and 9. Okay, so even though 3 was used a whole bunch of times, we only list it once. All right. Okay, now here we have, we're going to list the domain and range of each relation, and I'm actually going to do them, in the backwards order. I'm going to do C first. So for C, I can look at my X values, and I can see, because these arrows, that means it goes forever and ever to the left and forever and ever to the right. That means that any X value is going to work. So the formal way of writing this is, I'm going to say my domain is the set of numbers X such that X is an element of the real numbers. Okay, I will write that out in full. Let me just do that. Let me do that now. So what does this reads as? Domain is the set of numbers X such that X is an element of the real numbers. It's quite a mouthful, isn't it? Let me just do some highlighting here. The such that is that line, that horizontal bar or vertical bar. That means that means such that. And then here's the is an element of. And then the R here is the real numbers. Okay, so that's how we read that. Okay, and I can put the brackets, which covers up my my highlights, but that means is the set of numbers. Okay, that's what the brackets mean. Clear as mud, I know. Okay, let's do the range. Okay, so my range for this function, if I look at this, my range, my y never gets higher than 4 because there's nothing up there, but it goes down forever. So my range is the set of numbers y such that y is less than or equal to 4 and y is an element of the real numbers. There we go. All right. Let's do B. Let's do the domain first. So the domain, I'm going to write it down here because it doesn't quite fit. So the domain is the set of numbers X such that, now it's X in this case is between two numbers, so I write it down, not in the order that it goes in, if that makes sense. I move over a bit and I put my X here because I know that I'm going to describe my X. And it goes between -3 and 5. And then I have to decide, does it include those points? Well, this solid dot here means that it includes the -3, so I change my greater than to a greater than or equal to. And on this end, it doesn't include it, so I'm going to leave that blank. So I just want to sort of draw your attention to that. So there we go. Okay. And then to continue that, since it's a line, that means that it's all the numbers in between there, so it's X is an element of the real numbers. And my range is the set of numbers. My range, it goes from 0 to 4, so it's y such that y is between 0 and 4. But it does include both of those points. It includes the 0 because it includes the 0 here. And then it goes, anytime we get a point like that, that means that it includes that. And then y is an element of the real numbers. All right, there you go. I've got to pause it here. I'll come back later.